So this project is actually a collaboration with our department, so Digital and Smart Analytics, with also the Life and Health R&D team in the Swiss Re Institute. And it's about understanding the health progression of individuals. And maybe yesterday in the keynote, you have heard that actually it's a big thing for pharma companies, for companies providing healthcare services, but it's also a big thing actually for us. Why it's a big thing for us? Well, I mean, for a scientific conference, so I could drill down in the balance sheet numbers, etc., but it's a bit boring, I suppose. So long story short, Swiss Re is a provider for life and health reinsurance. And so we insure people actually for things that can happen in their lives. And this is a very long tail business, so things can happen within the next 20, 30 years, or even through their lifetime. And actually, to do a good job, so we need to know exactly when things can happen, or understand what things can trigger other things, etc. So that's why we are really interested in this, understanding this health progression things. However, there are many things that can influence, and it's really challenging problem to solve. The first part is basically there are some age effects. So, for example, not everybody is at the same risk of death at different ages and so on. There is also different risk factors that can come into play. So, for example, how people starting to smoke and so on, but also the prevalence of smoking, so how it will relate over time, etc. That can have quite a big influence if you want to simulate for the next 50 years. There is also some medical development, so some things that we have actually not observed in the data. So, for example, going forward, if there were some improvements in treatments or screenings, so that makes it quite complicated. And all in all, so, well, everything is a bit interacting with each other. So there is this double level, so to say. There is the population level and the individual levels to take into account. And well, it makes the problem really, really complicated in the end. So is there a way actually to handle all these kind of challenges, or is there a way to tackle this problem, so to say, in an ordered manner and try to solve it step by step? So our methodology is summarized on the right. So we decided to really build up a method that starts from the bottom up. So we really start from the individuals, and the idea is to understand really this health transition model, so to say. And once we know that, so we can basically simulate for each individual, things can happen for the next 50 years. Then we aggregate everything and we come up with some numbers for our portfolio, but also maybe some prevention measures for people, etc. So that's a bit more visual implementation. So again, we start with some individuals. We pull out this information from some medical data that is quite large that we have. And we assume that we have this transition model already pre-trained, right? And then the idea is, again, to take one individual, starting from some set of initial condition, we simulate many things that can happen. So if they continue to smoke or not, or if they start, if their BMI will get higher or lower, and how it relates into certain disease and eventually to death. And if we do that for one individual multiple times, then we can also do this for many individuals multiple times. And in the end, we can drill down for individual level, we can drill down for cohort level, and get a lot of insights actually out of that. So that's really helpful, hopefully. Before jumping into further into the modeling, etc., so I wanted to present you quickly how an individual looks like so far. So here you see the set of features of an individual. So it's fairly simplistic right now. So many things are very aggregated. For example, we don't really look at specific cancers, but we could, but so far it's just aggregated and we check the history. And the data we get is basically a longitudinal format. So we get a full history on a year-by-year basis. And the idea is really to predict the row after, right? And hopefully you would like to model this jointly. So you want to know, given the full history of this patient, how does the next year would look like? You would do this jointly, but it's a bit intractable. So we simplified this modeling with this approach. So in the end is to roll the information forwards on a step-by-step basis. And the first thing is to take the previous information and to update certain risk factors. And then these risk factors relate into disease. That's the third row. And then this disease could trigger death. And then we roll it over and over. And this is how we do the simulation, so to say, of the on a step-by-step basis. Now, you might understand that actually each of these boxes is kind of a model. So we have multiple models here. So we have 7 models. They have different types of outputs. So BMI is numerical, smoking is a multinomial approach, and the disease are basically binaries. So that's why we decided to split in each different types of models. So it's a bit easier to handle. We can drill down in each and every one. And also, it simplifies also the whole problem of not modeling everything jointly. But not everything is perfect. So for example, it's not a very causal model, so to say. There are some relationships, for example, cancer and smoking, that are not perfect in terms of causation. So since we observe both events at the same year, it's not really clear whether smoking is triggering cancer or cancer is triggering a smoking status, so to say, change. But that's how we do it for the first try. As I said, so each box is a model. So maybe let's drill down in each and every one of these models. Long story short, we train and test our model on data. So training set is from 2012 to 2014, and the testing is on 2015. We are mostly interested into population effects. So, for example, how age relates on overall to mortality, or how gender relates to mortality, etc. Not really into the individual effects, so to say. And also before, you might have understood that there is a lot of interaction. So, for example, how having a cancer and smoking and certain age might relate to death. You have to consider all these interaction effects into account. And it's a bit of a mess in the end. So we used a bit of a brute force approach using gradient boosted trees. And the advantage is that we don't have to take care of all these kind of things and all of these non-linearities. But on the other hand, you want to make sure that your model is fitting correctly, because what we care about is having the correct probabilities, and you want to make sure that not only your model does not overfit, but also it extrapolates or interpolates where you don't have so much data perfectly. So that's, for example, the case here. What you can see is basically the solid line is what the model predicts on average on our test set. And the dashed line is basically the rates of death, for example, you would observe in the data set. And in some specific cases, for example, when someone has a history of CVD and cancer, for low age, you don't really have data points there. And you want to make sure that really your model, doesn't care so much about these missing values, but still extrapolate in a way that you would expect. So here, for example, it's still flattens out, so to say, and it takes into account that for the low age, where there is a higher probability of death compared to age 10 to 20. So in the end, we didn't spend so much time into tweaking the model. We just put a lot of regularization, but we spent a lot of efforts onto the validation and understanding how the model captures relationships. And in the end, in terms of simulations, so we basically, as I said, we take the model before and we apply the recipe, so to update the risk factors and then the disease and then death. And this is how it looks like in practice. So we can, starting from some initial set of conditions, we do the simulations on stochastically. So we apply some Monte Carlo simulation approach. And basically we can apply this for a lot of individuals. So here, for example, we have only 2, And the only thing that is different is basically the second one has a history of diabetes, where the first one is healthy. And you can see here, again, across 50-year simulation. So each small line is basically a simulation, so things that can happen to this individual. And you can see that compared to these two persons, so the second one has actually a higher probability of death. You can see that across time, so both tracks start to converge more or less to the same point. So they are converging. And so the main difference is actually on the beginning, so to say, so this offset. And we can do this on a 1-year probability, but we can also try to see how their survival probability is going over time, etc. And we can do this not only for death, but we can do this for cancer, etc. So there is quite a lot of things to do. So if I want to summarize really in a nutshell, so our approach is fairly simple. But on the other hand, it's quite a scalable architecture. So we could even drill down further in the data, so split down certain disease, integrate some further risk factors. There are still some things to be done, I would say. So, for example, how to improve certain models, etc. But and it's also still fairly. I mean, there is some simplification, some hypotheses that we made that we might want to revise. But on overall, it's been a very exciting project, and it's been very cool to work on this. So if there is any question, I would be happy to answer. And I want to thank you for your attention and for your interest.